Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
Welcome back. This is our second lecture of chapter number 10, and that is about the secant formula. So in our previous lecture we discussed the column under centric axial load. So in this lecture we are going to discuss the eccentric loading. So first we will discuss what is eccentric loading. So you can see this is the column. For example, this is column having axis here, and if you apply a load that is at a distance of E from this center. So this is load P applied at a distance of E from this center. So this load is known as eccentric load, and due to this eccentric load there will be a moment that will be produced in this column. So if you can see, this is a column AB of length L, and that is acted upon by eccentric load P, and eccentricity is C. So where is E, where E is the distance between this load applied and the axis of this column. Now due to this loading and eccentricity, the column will buckle like this. So if you want to move this load P to the centric load, for example, if you want to replace this eccentric load, let this be the center, clear. So if you want to put the load into the center, axial center P, clear. So due to this is P into E, there will be a couple that will be produced, and this couple will be, let this couple will be M. Now you can see that due to this loading the column may buckle as well, but due to this eccentric loading there will be a couple, and due to this couple there will be a bending as well. So in order to analyze the effect of this load and centric axial load and the couple that is produced due to this eccentric load, we observe a section of this column. Let we take this section, and this section is at a distance of X from this point A. So that is also represented over here. This is a point A and P load is applied, so this X is the distance from this point A. Now due to this load there will be a deflection, clear, and this deflection is shown over here, that is Y. Again I will repeat, this P is the eccentric load that was moved toward the center, and we have already given the moment or couple that is produced due to eccentric loading over here. So if you want to analyze it, you can see that sum of all moment about point Q is equal to 0. So here the moment about this point Q is one moment which is due to this eccentric load, and this moment will be equal to P into E, because you can see here P is the distance and E is the perpendicular distance. So that is ME, and that is also over here MA is equal to PE. So one moment will be MA and other moment is due to this axial load. So it will be P into perpendicular distance is Y. So it will be, moment will be MA plus P, this movement is counterclockwise, it will be positive, and this will be again counterclockwise, so P into Y is counterclockwise, and there will be, if you cut the section over here, there will be again a movement, reaction movement as well, that is again shown over here. Do not draw it, clear. So at point A, this is the couple due to this eccentric load, P is the axial load, and this M is the reaction moment is as well. So I will also write this M as well. So their sum must be equal to 0. So it means that M is equal to minus MA minus P into Y. As this MA is equal to P into E, so it will be minus P into E minus P into Y. So this is the reaction moment at point Q. Now we can rearrange it. We can also write it M is equal to minus Py minus Pe as well. Now you know that we have formula, that is d square y over dx square into Ei is equal to moment. Again, if you are going to find d square y over dx square, so it will be equal to m over Ei. You can put the value of m, that will be equal to minus Py minus Pe divided by Ei. So if you further simplify it, it will be equal to minus Py divided by Ei and minus Pe divided by Ei. So it means that this d square y over dx square will be equal to minus Py over Ei minus Pe over Ei. So if I recall from our previous lecture, we said that P over Ei is equal to small p square. That was discussed in our previous lecture. So if P over Ei is equal to P square, so you can see that P over Ei is also available over here and it is also available over here. So we can write it as minus P square y minus P square E. So this equation will become equal to d square y over dx square is, you can bring it over toward the left side, so it will be equal to P square y is equal to minus P square E. So now you can see this is second order differential equation, and its general solution can be written as y is equal to a sine of px plus b cos of px minus e, where a b are unknown constant, and that can be obtained by using boundary condition. So let's move toward finding the boundary condition. So you can see this was a column, let's say this was a pin-ended column having x is this. So at first boundary condition was at x is equal to 0, y is equal to 0, and the second boundary condition was at x is equal to L, y is equal to 0. So this is x is equal to 0 and this is x is equal to L. So you can put the boundary condition in this general solution. As per the book, this equation is given as equation 10.24. So for your simplicity, I will use the same thing, clear, so that if you check the book, so that will not mess up with this lecture. Now you can put x is equal to 0, y is equal to 0 in equation to 10.24. So if x is equal to 0, sine will be 0, y will be 0 because y is equal to 0. I will do it for this condition. For this condition, y will become 0 and a sine of px. So sine of px will be 0. So sine of 0 is 0. So it will be 0. Plus b cos of p into 0, which is 0. So cos of 0 is equal to 1. So it will be only b minus e. So we can say that from here we can get b is equal to e. So we have obtained the value of b. Now for this boundary condition at x is equal to L, y is equal to 0. So you can put it 10.24. So if you put it, so 0 a sine of p into L plus b is equal to e. So it will be e cos of p into L minus e. So from here you can see that 0 is equal to a sine of PL and there is e common in them, or you can also write it as minus e plus e cos of PL. Again this a sine of PL will be equal to e minus e cos of PL. Since e is common over here, so you can get it e minus 1 minus cos of PL. So a sine of PL will be equal to this. Let this equation is equation 10.25. Now if you recall your knowledge of mathematics, so this sine of PL, this sine of PL can be written as 2 sine of PL over 2, where this L is the length of the beam, clear, into cos of PL over 2. And this term 1 minus cos of PL, 1 minus cos of PL, that can be written as 2 sine square PL over 2. Clear? Now you have this value as well and you have this value as well. You can put this and this in equation 10.25. When you put it, so definitely you will get A is equal to E tangent of PL over 2. This is the value of A. So now you have the value of B and A as well. You can put it in equation 10.24. So you can replace A and B with this value B and E. So you will put A and B in equation 10.24. So when you will put the equation, so this general equation will be equal to y and it will be equal to E tangent of PL over 2. Remember this capital L or small l, these are same. I will use small. Clear? So E tangent of PL over 2 plus B, and B is equal to E cos of P. Okay, one thing I have right. So you can see this is the value of A tangent of PL by 2 into sine of PX over 2. Sorry, PX. Plus B is equal to E and cos of BX, cos of PX minus E. So you can take E as common from all these. So if you take the common, so it will be equal to tangent of PL over 2 sine of PX plus cos of PX minus 1. So let this equation is 10.26. Clear? Now you can obtain the maximum deflection. So if you see it in this, so maximum deflection is over here, and it will be at a distance of x is equal to L by 2. At x is equal to L by 2 we have maximum deflection. So you can put here at, I will write it, at x is equal to L by 2 we have y max. So when you will put x is equal to L by 2, so you will get y max become equal to E into tangent of P L over 2 into sine of PL. Sine of P, and instead of Lx we will put L by 2. It will be equal to sine of PL over 2. Similarly, cos of PL over 2 minus 1. So this will be the equation of maximum deflection. Okay. So when you further simplify it, you can do it, you can check it in the book. So you will get in the simplified equation will become equal to secant of PL over 2 minus 1. So you have maximum deflection is equal to E into secant of PL over 2 minus 1. Now you know that this small p square is equal to capital P over EI, and so small p will be equal to under root P over EI. So you can put the value of small p over here, and you will get y maximum will be equal to E into secant of, instead of P I will write the equation of PP over EI, clear, into L by 2 minus 1. So let this equation be equation 10.28. So you can see that this expression, in this expression the y max will become infinite, and it will be when infinite when this theta, this whole is theta. So this under root P over EI into L by 2 is equal to pi by 2. Okay, so while the deflection does not actually become infinite, it nevertheless become unacceptably large, and P should not be allowed to reach the critical value, which satisfies that P critical is equal to pi square EI over L square. I will repeat it that this expression obtained indicate y maximum because, and this y maximum become infinite when this value will become equal to pi by 2. So the deflection does not actually become infinite, and it nevertheless become unacceptably large. So when the deflection is not infinite, so when deflection is not infinite, so P should not be allowed to reach the critical value. So your applied load should not exceed this value. Now you can see that under centric load we applied a load on a column that is under centric load, and the P critical was this. Clear? The maximum deflection in alternative form can be obtained if you put the value of P critical, like if you put the value of P critical in this formula. Clear? So when you put it, it will be equal to Y max is equal to E into secant of pi by 2 under the root P over P critical minus 1. So you can either use this Y max 10.28 or you can also use this equation, that this equation is 10.31 in the book. Now the maximum stress occur in the section of column where the bending moment is maximum is that, for example, this was the beam, this was the cross section of the beam. Let me draw it correctly. This was the P load, clear, and point A, and there was a moment MA which was equal to P into E, and here there was a load and a reaction moment. Now this moment is maximum at this C, at a distance of C from the neutral axis. So the maximum stress sigma max occur in the section of column where the bending moment is maximum, and bending moment is maximum at, if I draw the section, so this is axis, so bending moment will be maximum at a distance of C from the neutral axis. So this maximum stress here in this condition will be equal to stress due to this P by A plus the stress due to this couple or bending. There will be a stress which is equal to bending moment maximum into C divided by I. Okay, and from free body diagram of this portion AC, you can find that maximum bending moment is equal to P, and this was the original axis, this was the deflection Y. Clear? So the maximum moment will be P into maximum deflection, which was at a distance of L by 2 from the length of the axis, so P into Y max, and another moment is MA. Clear? So now you can put the value MA is also P Y max, and MA is P into E. So this maximum bending moment will be equal to P into Y max plus E. This is maximum bending moment. So you can put the value of maximum bending moment in this maximum stress. So you will get the maximum stress as P by A into 1 plus Y max plus E divided by I. Clear? Again, P by A is same, and this maximum bending moment is P into Y max plus P into E, and there will be a C as well. This will be R square. Y, I will simplify, I will write it over here. You can see if you put this maximum, this P by A will be there. I will write it, P by A will be there. this maximum bending moment will be plus py max plus pe into c divided by I. Clear? Now I is equal to, as we know that I is equal to AR square. Clear? So instead of this A will become equal to AR, I is equal to AR square. So you can write R square as I by A. I by A. So here you can put the I is equal to AR square. So you can put here I will write it P by A plus Py max plus Pe into C divided by I is AR square. Now you can see this will be Py max over A, this is P over A, and this is Pe when it will multiply by with C with Pe into C divided by AR square. So if you take P over A as common, so it will be equal to 1 plus Y max plus E into C divided by R square. I hope it is clear to you now. Okay. So now you know that you have the maximum value of Y max in equation 10.28. So you can put it in this equation. So you will get sigma max is equal to P by A into 1 plus EC over R square secant of under root P over EI into L by 2. Or you can also write it as sigma max is equal to P over A into 1 plus EC over R square into secant of pi by 2 into under root P over P critical. So this equation can be used with any end condition as long as the appropriate value is used for critical loading. So this is the maximum bending stress that will be created in the column with eccentric loading. Now, and this is also known as secant method for finding the stress in the eccentric loading. Now if you further look at the formula of this formula or this formula, so you can write it in term of P over A. So if I write it in term of P over A or this equation this equation, clear? So if I take this equation and rewrite in term of P by A, so P by A will be over here. So P by A is equal to sigma max divided by 1 plus EC over R square secant of under root P over EI into L by 2. Okay. Now we know that I is equal to AR square. Clear? So instead of I over here, I can also write it, this equation P by A will become equal to sigma max divided by 1 plus EC over R square into secant of 1 by 2 under root P over EA. Instead of I will write AR square, so A will be there and R square will be out, so it will be equal to L over R, and this L will be equal to effective length, where this effective length is applied for various end condition, and this equation is known as secant formula. Secant formula. Now E is eccentricity, C is the distance from neutral axis to the outermost edge. For example, if this is neutral axis, so C is this distance. Clear? P is the load, E is the modulus of elasticity, A is the area, L is effective length, and R is radius of gyration. So you can see that this P by A will be equal to this one. Now the stress sigma max in a column with effective slenderness ratio of LE over R for a ratio of EC over R square, where E is the centricity of the applied load. So P by A, this P by A appear in both members, so it is necessary to solve a transcendental equation by trial and error method to obtain the value of P by A. So this equation P by A is again used with the slenderness ratio, and we get a different curve that will be shown over you in next slides. So you can see this is LE over R, which is slenderness ratio, and this is P by A, and this is various value of EC over R square. This was the same maximum equation, maximum stress, and P by A is equal to maximum divided by this value. So these graphs can be obtained by taking various value of EC over R square with an effective length in order to find P by A. So you can see that for larger slenderness ratio, so you can see larger slenderness ratio and with EC over R square, this behaves like Euler curve. Clear? So larger length behaves like Euler curve. So here the yield strength will be your strength, critical stress or strength should not is exceeding the critical yield stress. So here the yield stress will be taken as the criteria for the failure due to compression in yielding. Now if you have the value of EC over R square is equal to 0.1 and you plot different value of LE over R, so you will get different P by A ratio that can be shown in this graph. So same is the case with different EC over R square value. You can see that the graph will be like this. So it means that this secant formula is effective for the medium or intermediate you can say intermediate length of the column. This graph is for foot-pound system and this graph is for metric system. Again, if you consider that EC for smaller value of LE over R. Clear? So we have P by A is equal to sigma max divided by 1 plus EC over R square. So if this LE over R is small, you are talking about this area. So if LE over R is small, so secant of this value will be equal to 1, and we will get sigma P by A is equal to sigma max divided by 1 plus EC over R square. And this value can be obtained by neglecting the effect of lateral deflection of the column. So for large value of LE over R, the curve corresponding to EC over R square get very close to the Euler curve, which I have discussed earlier. Clear? So the secant formula is mainly used for intermediate value of LE over R. However, to use its effectively, the eccentricity E of the load should be known, but unfortunately this quantity is seldom known with any degree of precision. Next is the sample problem 10.2. So in this problem it is given that uniform column consists of 8 feet section of structural tubing having the cross sectional is shown. So you can see this is a the cross section is shown, the length is 8 feet, and that is acted upon by a eccentric load in part A. The modulus of elasticity is given, and this tubular section is shown over here, which is 4 by 4 inch. All other values, area, its moment of inertia, is its radius of gyration, and C is the distance from neutral axis to the topmost. All the values are given. So first it is asked that using Euler formula and a factor safety of 2, determine the allowable centric load for column and corresponding normal stress. So we have to require allowable centric load and normal stress. In B part, assume that allowable load found in part A. So here you will use the allowable load that is calculated in part A to apply it at a point of 0.75 inch from the geometric axis of the column. So you can see this is geometrical axis of the column, and now the allowed load is applied at a distance of 0.75 inch from this axis. So determine the horizontal deflection of the top of the column and maximum normal stress. So you have to find the deflection of this column and maximum normal stress. So it's a very easy problem. Let's move to solve this problem. So in our part first, it was asked to find the allowable stress, and factor of safety was given as 2. Clear? So you can see that critical stress for this loading, for central loading, is equal to pi square EI over LE square. Now this load, this column is like a column whose one end is fixed while other end is free. So in that case, effective length is equal to 2L. So here this length is equal to 8 foot. So 8 multiplied by, if you want to convert it into inch, so 1 foot is equal to 12 inch. So it is 16. 8 feet. So it is not 2, it's 12. 12 8s are 96. So it is 96 inch. Clear? So LE will be equal to 2 into L. So 2 into 96 inch will be equal to 192 inch. So you can put, you have E value. Clear? That was given in the question. E is equal to this 29 into 10 raised to the power 6. So you have the value of E, you have I that is given, you have L over here. So you can put it, you will get the critical load will be this one. Now you know that factor of safety is equal to critical load divided by P allowable. So you have critical load over here. So you want P allowable, so P allowable will be equal to P critical divided by factor of safety. So P critical is 62.1 kips divided by 2, clear? So you will get P allowable is this one. Now you have P allowable, so allowable stress or normal stress is equal to P allowable divided by the area. So P allowable is 31 and area is given over here. So you can put and you can get the normal stress. So this was the answer of part first. Now we will move toward the part second. In part second, it was given that use P allowable that is obtained in part 1 and eccentricity of 0.75. So find the maximum deflection and the maximum normal stress. So you can see that maximum deflection, if you remember the formula of maximum deflection, so maximum deflection Ym is equal to E into secant of pi by 2 into under root P over P critical minus 1. Now you have P, which is this one 31.1 and P critical is 62.1. So you can take the value and you can put it. Remember that this secant, when calculating secant of this, so your calculator should be in radian, clear? So when you put it, it will give you the Y maximum. I will repeat that. Here you can see P over P critical, so you can see that factor of safety is equal to P critical over P. So here this is P over P critical, so P over P critical will be equal to 1 over factor of safety, which is equal to 1 over 2. So pi by 2 into here instant P over P critical, I can write 1 over 2. So if you further simplify it, it will be pi 2 into under root 2, clear, minus 1. So maximum deflection Ym, which is from the center, will be this one. Now maximum normal stress, for maximum normal stress we have formula sigma max is equal to P by A into 1 plus EC over R square into secant of pi by 2 into under root P over P critical, clear? So you have the value of E, you have C given, you have radius of gyration, P and P critical are also available, so you can put it in the formula and you will get the maximum normal stress is equal to 22 KSI. So this was all about secant formula and concept of eccentric loading on a column. I hope you have enjoyed the video and keep watching and learning more and more from this video. Thank you.